All right, so a couple of announcements. Reminder that we have our second exam this week, starting on Wednesday through Friday. And so we will have on Tuesday evening at 7 on Zoom, we'll have a question and answer session. So I will create the Zoom link and send that out either later today or sometime tomorrow morning. So you'll have that in plenty of time. And the review session that we filmed that on Saturday, so that is posted on Learning Suite as well. So you should take a look at that review session because that will help you have the questions to ask at the question and answer session. And there's a Bacon quiz on eliminations that becomes available today. So you can use that Bacon quiz as well to help you prepare for exam 3 or exam 2, or you can save it for the final exam. So we left off on Friday talking about the E2 mechanism. We showed you this energy diagram, and we showed you the transition state where we have several partial bonds, where we have intermediate hybridization and geometry going on here. So we'll continue our discussion of the E2 mechanism, and we'll talk about something known as Zaitsev's rule as part of that discussion. And then we will discuss the E1 reaction as well. So in an E2 reaction, a strong base is required. The base is participating in the rate determining step, and it needs to be a strong base in order to deprotonate an alkyl halide, in order to deprotonate one of the beta hydrogens of an alkyl halide. And we learned a definition of strong bases. We said that any base that is comparable or stronger than hydroxide would be considered a strong base. We're going to expand our definition of strong bases a little bit for E2 reactions because there are two nitrogen-containing strong bases that participate in E2 reactions. And they're known as DBN and DBU. These are abbreviations. The full names are much, much longer. So we will just use the abbreviations for these compounds in this class. So these are not as strong as hydroxide, but they are strong enough to participate in E2 reactions. So we're going to, as I mentioned, expand our definition of strong bases to include anything that's comparable or stronger than hydroxide plus DBN and DBU. So these compounds, most nitrogen-containing compounds that are neutral, such as ammonia, are weak bases. And these bases are stronger bases than ammonia or other amines, other nitrogen-containing compounds. They're essentially 100 times stronger than a normal amine or nitrogen-containing compound. So we do need to understand why that is the case, why these compounds are 100 times stronger than a typical amine. And the first step in understanding that is understanding which nitrogen is protonated. When this is functioning as a base, which nitrogen gets protonated? The sp3 nitrogen or the sp2 nitrogen? Okay. Any ideas? Yes, please. Yeah, each of these has an sp3 nitrogen and an sp2 nitrogen. Okay, so which one of those nitrogens is getting protonated, the sp3 or the sp2? Yes. Okay, so you're on the right track in terms of thinking about the hybridization. So sp3 has less percent S character than sp2. And if it has less percent S character, it should be further from the nucleus. So the lone pair should be more available, right? If that's all that was going on, then you would be correct. But there's another factor that overrules that. And we actually see protonation on the sp2 nitrogen. And I'll show you why. So if we're going to protonate, and it works for either of these bases, I'm just going to show it with DBU because that's the one I've drawn here on the right. If we protonate on the sp2 nitrogen, then something happens. I'm going to move the, actually I'll put the lone pair there. I didn't make my arrow long enough. I'll move this over. It's always more difficult to draw 7-membered rings than it is to draw 5 or 6-membered rings. Okay. So this is the conjugate acid of DBU where we've protonated on the sp2 nitrogen. Is there something about this conjugate acid that you notice? Is there something that we can do with this conjugate acid? Yes?
Well, it's going to have a bond, so in that case, I don't think they could resonance structure anywhere, but it should give more electron.
Okay.
It should provide more electron flow from this connection to
Okay.
balance the bond charge.
So you actually can draw a resonance structure because we have a lone pair adjacent to a pi bond. Whenever we have a lone pair adjacent to a pi bond, we can draw a resonance structure. So we can push the electrons onto the positively charged nitrogen. Okay. And so what we see is that through resonance, we can delocalize the positive charge. It can be shared by the two nitrogens. And so we get a much more stable conjugate acid if we protonate on the sp2 nitrogen. If we were to protonate on the sp3 nitrogen, we would no longer have a lone pair adjacent to a pi bond. We would have a lone pair on a pi bond or on an atom involved in a pi bond. You can't draw resonance structures in that case. You have to have the lone pair on an atom adjacent to the pi bond. Okay? So since you can have a resonance stabilized conjugate base or conjugate acid when you protonate the sp2 nitrogen, that's where these bases are protonated as opposed to the sp3 nitrogen because you cannot have a resonance stabilized conjugate acid in that case. So the pKa of the conjugate acids of DBN and DBU is about 12. We'll say approximately 12. So the pKa of water or alcohols, that's in the 16 range. So you can see that these are weaker acids, or sorry, stronger acids, and therefore the bases are weaker than water or they're weaker bases than hydroxide or the conjugate bases of alcohols, but they are still strong enough bases to participate in E2 reactions. Ammonia, the ammonium cation is pretty close to 10. So as I mentioned, DBN and DBU are about 100 times stronger as bases than ammonia is because the conjugate acids of DBN and DBU are 100 times weaker than the conjugate acid of ammonia is. So that makes DBN and DBU strong enough bases to participate in E2 reactions. Questions? So the book shows us an example of an E2 reaction involving DBN. And you see they protonated on the sp2 nitrogen. You'll see that they drew a curved arrow from the lone pair on the sp3 nitrogen so that when they drew the conjugate acid, they ended up with the resonance structure that I drew on the right as opposed to the resonance structure that I drew on the left. A principle of drawing mechanisms, when you are producing a product that is resonance stabilized, you can draw either of the resonance structures. It doesn't matter which one you draw. So the way that the book drew it is perfectly acceptable. You could also leave out this little curved arrow right here, and then you would have drawn the resonance structure on the left as opposed to the resonance structure on the right. Okay? Either one of those would be correct. But you have to use the curved arrows that correspond to the resonance structure that you draw in order for it to be correct. Any questions about that? Okay, so you do not have to memorize the structures of dBn and dBu. If you're going to use them on a problem, you can just write the abbreviations and we'll know what you mean. But if you're given the structures, you should be able to explain what I've explained to you today. Namely, why are they stronger bases than normal amines, such as ammonia, and which nitrogen gets protonated? Okay, that's an explanation you should be able to give if you're provided with the structures. Okay? All right, so let's talk about a couple of other issues related to E2 reactions. Let's talk about the leaving group. How does the leaving group affect the rate, or does the leaving group affect the rate of an E2 reaction? Okay, I see nodding of heads. Why does the leaving group affect the rate? Yes. It makes sense, yes. Okay, it's second order, yes. Okay, both the reactants are participating. Yeah, you want to elaborate on that? Okay, yeah, faster reaction because the leaving group is breaking in the rate determining step, or the leaving group is leaving. The bond between the leaving group and the carbon is breaking in the rate determining step. So it stands to reason that the better the leaving group, the faster the reaction will be. So our fluoride is going to be the worst. We're not going to see fluoride function as a leaving group in any of the reactions in this chapter. So chloride will eliminate slower than bromides, and iodides will be the fastest because at the transition state, you have a partial negative charge on that leaving group as you have partially broken that bond. And that partial negative charge is going to be more stable on the less basic leaving group. Okay, so that's why we have this relative rate data. Okay, what about solvents? What kind of solvent would be the best for an E2 reaction and why? Yes, please. Okay, we want a polar aprotic solvent because the polar aprotic solvent will not solvate our base. We know that polar aprotic solvents will solvate cations. They will not solvate anions. Our base, in most cases, is going to be an anion. And so if it is solvated, it's going to react more slowly. So polar aprotic is going to be the best. No solvation of the base is the reason for that. Okay. So another factor that we have is the type of alkyl halide, primary, secondary, tertiary. Which types of alkyl halides would react faster in an E2 reaction, more substituted or less substituted? Okay, so you're saying more substituted alkyl halides would react faster. Why do you believe that?
Because they'll be able to distribute the negative charge better.
Okay, which negative charge would that be?
The negative charge that comes when you take off the hydrogen and then it has to, when it's creating the pi bond.
Okay. Yes, so you have negative charges. The negative charges are going to be on the leaving group and then on the base, right?
Yeah.
So those are not really close enough to the alkyl group, but what we have is the other thing you mentioned at the transition state. What did you mention as part of the transition state? The partial double bond, okay? So what what can stabilize double bonds? Yes. Okay, so the sp2 hybridized carbons of alkenes are electronegative. They're going to be they're going to want to attract electrons. So if we have electron donating groups bonded to our alkene, then that will stabilize our alkene. Okay, so it is indeed stabilizing the transition state. What it's stabilizing is that partial double bond that is forming. Okay, so note that we have to be careful in our discussion and our description. It's not the fact that those alkyl groups stabilize the alkene in the product that matters. It's that they stabilize the partial alkene in the transition state. That's what lowers the activation energy and makes the reaction faster. Because these eliminations, these E2 reactions are irreversible. Right? Once we have our halide leaving group lost, we're not going to go back and make an alkyl halide from an alkene. That's just not going to happen. So so it's not necessarily the more stable product that's going to be the major product. It's the product that's formed the fastest that's going to be a major product. So when we're looking at an alkyl halide, a primary alkyl halide in this case, that's going to give us a monosubstituted alkene. So at the transition state, we have one alkyl group that's donating electrons to that partial double bond that's being formed. And then we can compare that to a tertiary alkyl halide. And we deprotonate one of the beta hydrogens. And in this case, we end up with a tri-substituted alkene. Okay? So at the transition state, we have three alkyl groups donating electrons to the partial double bond. At the transition state, forming the monosubstituted alkene, we have one alkyl group donating electrons to the partial double bond. So the transition state leading to this tri-substituted alkene will be lower in energy than the transition state leading to the monosubstituted alkene. Okay? So we have to go back to the transition states and make arguments about relative stabilities of the transition states to explain that the reaction with the tertiary alkyl halide will be faster. Okay, so tertiary alkyl halides will react faster in E2 reactions than secondary alkyl halides, which in turn will react faster than primary alkyl halides. Okay? Any questions about that order? Yes, please.
In the one you drew on the bottom, did you use,
So we deprotonate. No, yeah. So sometimes it's hard to figure out exactly how many carbons you'll have in the product because we're losing a hydrogen and a bromine, but not any carbons. So a good way to make sure you haven't made a mistake is just to count the carbons in the alkyl halide and make sure that they're all here. So we've got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. Okay. So I'm glad you commented on that because it's a common mistake that students make on exams is getting the wrong number of carbons when they draw a product compared to the starting material. So you'll want to make sure you check that when you're taking your exam, count your carbons. Okay, so let's talk about something that is known as Zaitsev's rule. And this was discovered by a Russian chemist named Alexander Zaitsev. And he was performing chemistry in 1875 in Russia at a university called Kazan. And he was studying dehydrohalogenation reactions. He was studying the types of eliminations that we're studying in this class. And he noticed something. So when he performed a dehydrohalogenation of an alkyl halide, such as the one I've drawn for you here, that has two different types of beta hydrogens. We have the beta hydrogens here and we have the beta hydrogens on the methyl group, there are two possible constitutional isomers that can form from this reaction. So Zaitsev ran this reaction, or one very similar to it, and what he observed was that the more substituted alkene was the major product, and the less substituted alkene was the minor product. Okay? So why is that? That was an empirical observation that he made, and he published his results, and so he got this rule named after him. But we need to be able to understand and explain why this is the case. Why is the more substituted alkene the major product? Yes, please. Why the more substituted alkyl halide reacts faster? Very, very, very similar explanation, yes. Okay, so the difference here is that in this case, we have one alkyl halide and two reaction pathways leading from that alkyl halide. Whereas up here, we had two different alkyl halides, each of which gave a single product. So here we have one alkyl halide with two reaction pathways, two transition states leading from that alkyl halide, giving two different products, okay? And so the pathway to the major product is lower in energy and has a lower energy transition state because there are more alkyl groups stabilizing the partial double bond in the transition state. Okay, we have three alkyl groups in our major product, two alkyl groups in our minor product. So we have a lower energy transition state leading to the major product. Therefore, it is formed faster than the minor product. Okay, question? Yes. Yes, we have two methyl groups, and those are identical. And so it doesn't matter which one of those we would remove a hydrogen from, we would get the same product. But notice that there's a total of 6 beta hydrogens on these methyl groups, and there's 2 beta hydrogens here, yet the removal of the one with the fewer beta hydrogens still gives us the major product. Right? And that's because of that lower energy transition state that we have. Okay? So a very similar explanation to the one we gave for why more substituted alkyl halides react faster than less substituted alkyl halides in E2 reactions. So this particular reaction I've drawn for you is an example of what we call a regioselective reaction. Okay? A regioselective reaction is a reaction in which more than one constitutional isomer is possible, but one of those constitutional isomers dominates or is formed exclusively. Okay. So we have 2 possible constitutional isomers. We have a major product, one that dominates over the minor product. So the E2 reaction is a regioselective reaction. Okay. The more substituted constitutional isomer will be the major product. Okay. And it doesn't really matter if it's the major product or the only product, we'll treat that the same, right? In most cases with dehydrohalogenations, you would see at least a small amount of your minor product, but we're not going to worry about what those ratios are or whether it's all of one and none of the other. We're just going to say that usually on a test, we'll just ask you to draw the major product, and it doesn't matter if it's the only product or the major product. We would treat that the same, okay? All right, so when we have more than one constitutional isomer that's possible and one dominates or is formed exclusively, that is known as a regioselective reaction. But we have other types of dehydrohalogenations where we have more than one stereoisomer that is possible. So let's draw an example of that. let's take this alkyl halide where we have just one type of beta hydrogen over here. But if we react this with a strong base, like our sodium or potassium tert butoxide, it wouldn't matter. We're going to form a 1,1 disubstituted alkene. Or a 1,2 disubstituted alkene, sorry. And when we have a 1,2 disubstituted alkene, we have trans and cis isomers. We have stereoisomers that can form. Wow. Somebody's blowing stuff up, I guess. Okay. So here we have two possible stereoisomers. Is there going to be a major product? And if so, which one? Okay, nodding of heads. Yes, Claire? Okay, good. Less steric hindrance in which species? Okay, there's definitely less steric hindrance in the products, but what matters at making this the major product is that there's going to be less steric hindrance in the transition state. Okay, so this is our trans isomer, and that will be our major product. This is our cis isomer or diastereomer, and that will be our minor product. So when we make it all the way to the products, these groups are all planar, and it's really clear to see that if you have these two groups in the same plane, they're going to be really close together, and you're going to have steric hindrance. At the transition state, it's somewhere between tetrahedral and planar, so the steric hindrance would not be as great as in the products, but there would be enough steric hindrance due to the flattening of the geometry, the partial double bond, that the transition state leading to the cis isomer will be higher in energy than the transition state leading to the trans isomer. Question?
Is there a name for this? Like this is only the part that you read?
It doesn't, so yeah, it doesn't get a name like Zaitsev's rule, but it does get a name in that it is referred to as a stereoselective reaction. Okay. So in a stereoselective reaction, more than one stereoisomer is possible. But one dominates or is formed exclusively. Okay. So the example over here is regioselective. More than one constitutional isomer is possible, but there's a major product. And then the example over here is stereoselective. More than one stereoisomer is possible, but there is a major and a minor product. So depending on the type of alkyl halide you have, the E2 reaction can be regioselective in some cases, and it can be stereoselective in some cases. Any questions? Okay, so now you should be able to, well, let's look at this table here first before we do that. This table summarizes those characteristics that we've gone over with the E2 mechanism. And the kinetics, of course, are experimentally determined. More substituted alkyl halides reacting faster. We explained that here on this upper board. We talked about the base, the leaving group, and polar aprotic solvent. So you should be able to explain these bullet points in this table, much like in the other tables we've gone over. And you should also be able to look at a reaction and predict the major product based on what we've discussed today. So go ahead and pull your iClickers out. Go ahead and talk to your neighbors and select the major product, if there is a major product, in this reaction. Okay, any more answers coming in? Okay, that looks like all the answers. All right, so we'll go ahead and stop that. And before we discuss it, sorry, there's a follow-up question. Okay. Is this reaction regioselective, stereoselective, both, or neither? Okay. Okay. Get our final answers in. A couple more seconds, maybe. There we go. We had 18 on the first one, so that should be everybody. All right, so let's go back to the first one. Who would like to tell the class, raise their hand and tell the class which one is the major product and why they decided that? Okay, Claire? Okay, so you preferred B over A because B was more substituted. The alkyl groups can stabilize the partial double bond in the transition state. And then you preferred B to C because B is trans and C is cis, and there'd be less steric strain or steric hindrance in the transition state leading to B. Very good. That's exactly correct. And so is the reaction regioselective, stereoselective, both, or neither? It is both. So there are some cases where E2 reactions can be both regioselective and stereoselective if there are both more than one constitutional isomer and more than one stereoisomer possible. Then you can have a reaction be both stereoselective and regioselective. Any questions? All right, now we need to talk about the E1 mechanism. So just like with substitution, where we had two different mechanisms, SN2 and SN1, with elimination, we have two different mechanisms, E2 and E1. And I've drawn an example of an E1 reaction here on the board. And you'll see that in all E1 reactions, you'll see three things. You'll have tertiary alkyl halides. It's technically possible with secondary alkyl halides, but it's pretty rare, very, very slow. So most E1 reactions you'll see will be tertiary alkyl halides. You'll always have a good leaving group, such as an alkyl halide. And you'll always have a weak base in an E1 reaction. Okay, so that's what we've seen here. We're using water as our weak base to promote elimination in this case. So the 1 refers to the first order kinetics. The E1 reaction involves first order kinetics. The rate determining step only involves the alkyl halide. The concentration of the base does not matter. So what does that tell us about our rate determining step? What do we think is happening in our rate determining step? Yes? Okay, so what kind of reactive intermediate will we be forming? A carbocation. So the only thing that can happen with just our alkyl halide is loss of the leaving group and formation of a carbocation. So that's what's going to happen first. That's going to be slow. Giving us a carbocation. Notice this is the same rate determining step we have in the SN1 reaction. We generate a carbocation in the SN1 reaction. But the fate of the carbocation in the E1 reaction is different. What's going to happen is that we'll react it with our weak base, which will deprotonate one of the beta hydrogens, forming our alkene. And then we're going to get the conjugate acid of our base. This plus sign does not apply to the alkene. It just means that we have these two products. Okay? So two-step mechanism where the rate determining step is carbocation formation. That mechanism is consistent with the first order kinetics that we observe in this reaction. So we can look at an energy diagram for the E1 reaction. And we see that the first step does indeed have a higher activation energy than the second step. That's what we would expect. We have two transition states because we have two steps. And the first transition state, according to Hammond's postulate, is going to resemble our carbocation more than it resembles the alkyl halide. So this carbon-iodine bond will be mostly broken at the transition state. We will have mostly, the partial charges will be closer to 1 than they will be to 0. And then we have this second transition state where we are deprotonating one of the beta hydrogens of our carbocation. This transition state will also look more like the carbocation than it looks like the products, but it will have enough of a partial double bond here to have an impact on the outcome of the reaction, as we'll talk about in a couple of minutes. So as we look at this diagram and consider this mechanism, what types of alkyl halides do you think would react faster in an E1 reaction? More substituted or less substituted? More substituted. Why? Okay, so we're forming a carbocation in our rate determining step, and we know that more substituted carbocations are more stable. Because of Hammond's postulate, we say that this transition state closely resembles a carbocation. So the more substituted transition state will be lower in energy than the less substituted transition state. So what we will see is tertiary alkyl halides reacting faster than secondary alkyl halides. And because we're forming a carbocation intermediate, we will also say that primary alkyl halides will be unreactive because the primary carbocation is too high in energy to form. Okay? So we have the same trends that we had in the E2 mechanism, where more substituted alkyl halides react faster, but it's a different explanation because the rate determining step is different. In the E2 reaction, we said that the additional alkyl groups were stabilizing the partial double bond at the transition state. In the E1 mechanism, we're saying that the additional alkyl groups are stabilizing the partial carbocation at the transition state. So different rate determining steps, slightly different explanations. And then also in the E1, we know that we won't have primary alkyl halides participate because that carbocation is too high in energy to form. Okay, so another thing, another factor in the E1 reaction is that it will only happen with a weak base. What would happen if we treated an alkyl halide with a strong base? Yes? Exactly, okay? So this is not a scenario where the weak base is favoring E1. What's happening is that the weak base is preventing E2 from happening. The base would have to participate in the rate determining step, and a weak base is not strong enough to deprotonate an alkyl halide. So you have too high of a barrier for E2 with a weak base, and therefore you have to sit around and wait for the carbocation to form, of which now the weak base is able to deprotonate. Okay, so the reason weak base is required for E1 is because a strong base would undergo the much faster E2 reaction. Questions? Yes? Okay. So, I mean, technically you would say that it's a salt, right? Because you have the anion, iodide, and the cation H3O+. So you could say that they form a salt, but they're usually you're using water or using a mixture of water and an alcohol. You're typically using polar aprotic or polar protic solvents in these reactions. And so those salts are usually dissociated because they're solvated. Okay, so it doesn't really matter if you think that they're forming a salt together or they're separated ions. That doesn't really impact the formation of the organic product. Okay, good question. So what about regioselectivity? If we were going to form more than one constitutional isomer in an E1 reaction, which step would determine the major product? Step 1 or step 2? Step 2, exactly. Step 2 is where you're deprotonating. So if you had more than one type of beta hydrogen in your carbocation, depending on which one you deprotonated, you would get one product or another. Okay. So the E1 reaction is generally regioselective, and it does generally follow Zaitsev's rule. Okay, meaning that the more substituted alkene would be the major product. If you look at this transition state, I told you that it only has a small amount of a partial double bond because this transition state looks more like the carbocation than the product. But because the more substituted alkene would be the major product, there's enough of a partial double bond there to give enough of an energy difference to cause the more substituted alkene to be the major product. Okay, so this will follow Zaitsev's rule due to the presence of that partial double bond in the transition state of the second step in the reaction. Okay? What kind of solvents do you think would be good for an E1 reaction? Protic or aprotic? Okay, I'm hearing protic. Why? Yes. Solvated. All right, solvation of the base doesn't matter. Good. Good. The polar protic solvent can solvate both the iodide leaving group and the carbocation. So it solvates both products of the rate determining step. So the polar protic solvent is going to be preferred for an E1 reaction. So we have a table here which summarizes this information we've gone over in the last 10 minutes or so. And the results here in this table should look very familiar to you. They're very similar to the results from a table of another reaction we've studied. Which one? SN1. Yes, these are very, very similar. All you'd have to do is replace the word base with nucleophile, and you would have the same table that we had for the SN1 reaction. Okay? So the SN1 and the E1 reaction are very similar. They involve the same rate determining step, the same reactive intermediate. They only differ in what happens to that reactive intermediate. And the fact is that they're competitive with each other, meaning that when we're performing an SN1 reaction, we're also going to have an E1 reaction occurring simultaneously. When we're performing an E1 reaction, we're going to have an SN1 reaction going along simultaneously. So the unfortunate truth is that neither SN1 nor E1 are really that useful in the lab because you get mixtures of products. You get substitution and elimination. So if we take a tertiary alkyl halide, and we wait for the leaving group to leave and generate our carbocation. In this chapter, we've seen that leaving group get deprotonated by a base, a weak base such as water. Okay, and that gives us an alkene. But in chapter 7, we saw that our carbocation can be attacked by a weak nucleophile, and water, as well as alcohols such as methanol or ethanol, are weak nucleophiles in addition to being weak bases. Okay, so the water doesn't have to deprotonate our carbocation. It could also attack the carbocation. And then in the case where it attacks and performs the substitution reaction, then we need a third step, an acid-base step, to generate our alcohol product, and we get our H3O plus byproduct, which we also get up here. Okay? So both of these processes occur competitively and simultaneously, which again makes the E1 reaction less useful, much less useful than E2. The SN1 reaction is slightly more useful than E1 because if you have an alkyl halide that has no beta hydrogens, then it wouldn't be able to undergo E1. It could only undergo SN1. So there are some cases where SN1 is useful and is something you would do in the lab, but E2 is much more common than E1. Okay, question? So, right. So it's simply because in the elimination, that species is functioning as a base, whereas in the substitution, it's functioning as a nucleophile. Okay, water is both a weak base and a weak nucleophile. And I'm just referring to it as a base in the elimination because that's what it's doing. It's deprotonating a hydrogen, whereas in the substitution, it is attacking an electrophile. Okay? So we can look at this table here comparing E1 and E2. And the first bullet points in each case are quite true. E2 is much more common and useful. E1 is much less useful because you get a mixture of substitution and elimination. How do you ensure that E2 occurs as opposed to E1? You use a strong base, exactly. So if you want elimination, you're going to want to use a strong base because then you can get E2 and you can bypass this issue of E1 and SN1 occurring simultaneously. So, and of course, E1, as I mentioned, does not happen with primary alkyl halides. And E1 is not really favored by weaker bases. E2 is prevented by weaker bases, so E1 is the only alternative that you are left with. So you might wonder, why are we learning about E1 if it's not useful? It's not useful in the lab, but it's useful in the classroom because the E1 and the SN1 mechanisms help us teach important topics such as carbocation structure, relative stabilities of carbocations, Hammond postulate, all these sorts of concepts that we learned in the context of E1 and SN1 reactions are valuable. And so we use a reaction that's not synthetically useful, but is useful for teaching those principles. Okay? Any questions about the comparison between E2 and E1? All right, so we've got a couple more topics to finish on Chapter 8 on Wednesday. And then we're going to talk about, we're going to tie Chapter 7 and Chapter 8 together and we're going to talk about how we can predict when substitution will occur and how we can predict when elimination will occur. And hopefully we'll see you at our Zoom question and answer session tomorrow evening.